Okay, I saw that the video camera shut off. Again, we were finishing problem number 9 here, and I'm not exactly sure where it cut off, so if we didn't see it before the last segment ended, the enthalpy of this reaction was negative 1277.1, simply carried out the combination according to Hess's law of adding together the product energies and subtracting the reactant enthalpies of formation. Okay? All right, what do we have for number 10? We've got enthalpy of formation. What is the amount of heat released when so many grams react to produce ammonia? Okay, so we've got some stoichiometry involved here. So we need a balanced equation to do this reaction. So when we form a single mole of ammonia, a single mole of ammonia, NH3, so that we can use the enthalpy of formation value that we're given in this problem, which is negative 45.9 kilojoules per a single mole of ammonia. This is going to be a little bit different, but our reaction would be 1/2 of a mole of nitrogen, right, plus 3/2 of a mole of hydrogen gas to produce our ammonia. Okay. So this is a limiting reactant problem. We'd like to know what is the energy produced when we've got these two different quantities. Now, there's a typo I see in this problem. The nitrogen should be a gas. All right. So what we have to do anytime we're faced with a limiting reactant situation is determine which is our limiting reactant, and we're going to do that here by just calculating for each quantity the Q, and the smaller Q would be associated with the limiting reactant. Just like in chemistry 1, you could take each reactant quantity and figure out what product quantity would be made, and the smaller product quantity is the one that would actually be made, right? Because your limiting reactant would run out. So if I do this for the nitrogen, N2, all right, the mass of nitrogen that we're using is 5.38 grams. I need to convert that to moles. A mole of nitrogen is 28.02 grams. And then I would multiply by the negative 45.9 kilojoules. Now here's where that's sneaky, because that's per 1/2 mole of nitrogen, or 0.5 moles of nitrogen. Right? Just like in a problem that we had earlier when we had to reference the coefficient, unless we're going to change everything and scale these all up, in which case the energy would scale up, it's perfectly fine to take this quantity of energy as long as you associate it with this coefficient of nitrogen. All right? And so it does make your numbers a little bit sneaky, but you got to take 5.38 divided by 28.02 times 45.9, all negative, and then divided by 0.5. So multiply by 2. And I get negative 17.6 kilojoules can be produced if all of the nitrogen is used. Now we repeat with the hydrogen quantity, so 3.32 grams of hydrogen. Of course, hydrogen has a much smaller molar mass. A mole of hydrogen is only 2.016 grams. The same negative 45.9 kilojoules would apply, but now it would be in association with 1.5 moles of hydrogen. So we'll take our 3.32 divided by 2.016 times the 45.9 divided by 1.5. And if all of the hydrogen is used, negative 50.4 kilojoules of energy could be released. So our nitrogen is our limiting reactant, and the quantity of energy that can be evolved is the 17.1 kilojoules, or 17.6 is what I seem to have in the, 17.6 kilojoules of energy can be released. All right. All right, that looks like it wraps up the chapter 6 questions. We had them on this sheet first. Now we're going to look at 11 through 16. These are going to be our chapter 5 gas law problems. So number 11. The lid is tightly sealed in a rigid flask, 3.5 liters of hydrogen, 17 degrees Celsius, 0.913 atmospheres. The flask is heated. What's the pressure? So this is some code language here. Keywords. A rigid flask. Its volume is not going to change. So technically I could be using my combined gas law here. But the volumes are going to reduce or drop out because they're equal. So we're asked for what's the new pressure in this flask. So P2 will be P1 times T2 divided by T1. So our original pressure was 0.913 atmospheres times our second temperature. Now we have to put these temperatures into gas laws. So 71 plus 273 is 344 Kelvin. So we have to put the temperatures into gas laws. I meant to say we have to put the temperatures into Kelvin to use them in our gas laws, owing to the fact that negative temperatures exist on the Celsius scale, which means it's not an appropriate scale for gas law work. And then our original temperature, our 17 plus 273 is 290 Kelvin. Okay. So now we just need to crank this calculation out. 0.913 times the 344 divided by the 290, and we get 1.08 atmospheres. Does it make sense? Pressure and temperature are directly related, so as the temperature was raised for this cylinder or this flask, the pressure should have increased, and sure enough it did. Okay. All right, number 12. We've got a flask with some methane in it. We're given the temperature and the pressure. What's the pressure if the volume is increased and the pressure is decreased? So another application of the combined gas law. This time, all the variables are in flux, all right? And so we won't cancel out anything. And we're asked for, again, P2. So we've got P1, V1, T2 divided by T1 and V2. Okay. So we just need to get everything into the right position here. So in number 12, our original pressure, all right, is 318 millimeters of mercury. And it's fine if we leave this in millimeters of mercury. The question has not specified use atmospheres or answer in atmospheres. Our volume was 0.225 liters. Our new temperature, our second temperature, 95 degrees Celsius. So that's 368 Kelvin. Our original temperature for this gas was 27 degrees Celsius, so 300 degrees Kelvin. And our new volume is 0.5 liters. Okay. Now if we want to rough out what our answer might be, the volume increased, so the pressure should decrease according to that. And the temperature increased, which should cause a pressure increase. So there is a sort of conflicting trends there, although the volume more than doubled here. The temperature did not double from 300 to 368. So the volume is the dominant change in this context, and so I would predict a pressure decrease due to that volume increase. But let's find out. 318 times 0.225 times 368 divided by 300 and divided by 0.5, we get 176 millimeters of mercury. So our pressure decreased, again, largely driven by that volume increase that we see. All right, 3/4 of the way there. 13. We've got a flask with a certain volume and a pressure defined. We know the same number of moles as in another flask. What is the temperature if the SO2? All right. So if a 3.44